What's up, geometry students? We are getting into trigonometry. It's uh it's just a study of right triangles. Just focus our attention. We started with just like similar shapes last unit. Now we're just gonna like really dive into right triangles. A study. 1035. A study of right triangles. Okay. Because right triangles are mathematicians' favorite friends, architects' favorite friends, because it's got um, you know, every right triangle shares one angle, like if you say it's a right triangle, it's got a right angle. It's got a 90-degree angle. And what's fun about triangles is if you already know one, all you need is one other, and boom, you have the third because all the angles have to add up to 180. So the idea that we have going on from last unit is like the concept of scaling things. All we're going to be doing here is scaling right triangles. Okay. But to be able to refer to like the ratios that we're going to talk about, like let's say this is J, K, and L. Like if I say A over C, you know that A over C, if this is the same triangle with the same angles, that'd be equivalent to J over K. Instead of saying, oh, let's talk about the ratio of the opposite over the hypotenuse. Oh, you mean J over L in this case, the opposite over the hypotenuse. We use these shortcuts. Sine, cosine, tangent. These are all just shortcut ways to refer to the ratios that exist in these right triangles. And we use the mnemonic SO, CA, TOA. And when I say, hey guys, let's talk about the sine of angle A. Well, I'm referring to the ratio of the opposite side divided by the hypotenuse when referring to angle A. And so you would look at this triangle and you'd be like, oh, you mean A over C. Now you got to understand the hypotenuse is never the opposite, it's never the adjacent. The hypotenuse is the hypotenuse. You'd be like, oh, cool, A over C. Well, if this triangle had the angle A, this would be J over L. Like I'm just talking like, so any triangle with this angle, whatever this measurement is, let's say it's 20 degrees. Any triangle with a 20-degree angle will have to have this ratio A over C. And that'll equal J over K. And if you know the ratio, boom, you can like scale it. And that's all we're doing is we're just like talking about ratios of triangles with angles, right triangles with angles. That way we can scale things. Um, Cosine refers to the adjacent side over the hypotenuse. If I ask you, hey, what's the cosine of A? I'm just talking about the ratio in the right triangle with angle A. That's the adjacent over the hypotenuse. You'd be like, oh, that's B over C. And, if I was talking about this one, I'd be like, oh, B over C's got to equal K over L because these are similar. They both have angle A. So if you got B over C, oh, K over L is going to be the same. And once we start dealing with numbers, you're going to see how they're the same. Now, really quickly, be careful out there. If I'm talking about a different angle, then this would be the opposite of B. This would be the adjacent to A. So it's like the adjacent to A would be the opposite of B, and vice versa. The opposite to A would be the adjacent to B. So the sine of B, which refers to the opposite over the hypotenuse with respect to that angle, the opposite would be this, and the hypotenuse would be that. So we'd say it's B over C. Okay. And you notice like, oh, wow, they're the same. It's like, of course, we're talking about the same triangle. So you'll see like some of the ratios are going to be the same. Cosine, which is adjacent over hypotenuse. So the adjacent over the hypotenuse is C. What's the adjacent to B? Well, we'll call this length A is the adjacent side length of B. And you'd say like same thing, J over L would equal. We'll see more when we get to numbers, how things work out. The tangent of A is A over B. That's opposite over adjacent in SOHCAHTOA. We use this mnemonic to help us. Opposite over adjacent. So opposite is A and then adjacent is B. The tangent of B would be flipped. The opposite over the adjacent would be flipped B over A. Cool. This is just getting us used to, when I say the sine of an angle, I'm referring to the ratio in the right triangle of the lengths with respect to that angle. So first thing is first, locate the hypotenuse. Write down SOHCAHTOA. Here is Z. This would be opposite Z. This would be adjacent to Z. This is the hypotenuse. It's never opposite. It's never adjacent. Okay. We refer to the side lengths, the ratios of the side lengths, like we did last unit. The sine of Z, Q over T. The cosine of Z would be R over T. The tangent of Z would be Q over R. The sine of W, opposite of W is R. The hypotenuse is T. Cosine of W is Q over T. Tangent of W is R over Q. Cool. So that's getting us used to SOHCAHTOA. Now let's start seeing how these work with numbers and how like we understand scaling and how scaling with right triangles is actually very easy to do, which is why mathematicians like studied and used it so much. Okay. So we got this right triangle. We got this angle D. We got this side length 3, this side length 5. Well, this is not the side length, this is the hypotenuse. We know that the great thing about right triangles is the Pythagorean theorem. So we can do 3 squared plus b squared equals 5 squared. We could realize that this is going to be a 3, 4, 5 right triangle. Cool. Now, here's what's great. What's the sine of D? Well, the sine of D would refer to the ratios of the opposite over hypotenuse of a triangle with this angle D. Whatever this angle measurement is, it's like this would be the ratio of the opposite over the hypotenuse. This is 4 over 5. Cool. What's the cosine of D? 3 over 5. Now, watch this. What is 4 over 5? Well, it's 0.8. Or we could write it as 0.8 over 1. What's 3 over 5? Well, isn't that 0.6? Watch this. If I give you this ratio, you could immediately be like, oh yeah, if you have angle D, the ratio of the opposite side length to the hypotenuse would be 0.8 to 1. And the ratio of the adjacent side length to the hypotenuse would be 0.6 to 1. We have just kind of understood the ratios help you scale things. Look, this triangle is the same as this triangle. It's just divided by 5. 3 divided by 5. 4 divided by 5. It's kind of like the ratios help with you understand the scaling. And now we could take this and scale it. We could take this and scale it. It's like scaling is very important. And right triangles are very important. So we're just combining the two this unit. Now let's go to this. The tangent of D is 4 over 3. The tangent of E would be 3 over 4. Now watch this. This is great because this is 0.75 over 1. This is 1.333. But watch this. I can create another triangle with angle E where the opposite is 0.75 and the adjacent is 1. Oh, that's like taking this triangle and dividing it by 4. Oh, and watch this. If you could take 0.6 and divide it by 0.8, you'd get 0.75. So it's like understanding the ratios, understanding scaling. That's it. And sine, cosine, tangent is just a shortcut way to refer to those ratios. Sine of E would be 3 over 5. Cosine of E would be 4 over 5. Find this side length. 5 squared plus 12 squared equals c squared. 25 plus 144 equals c squared. 169 equals c squared. C equals 13. Cool. We're going to start scaling too. Why don't we just start scaling right away? Like, you could divide everything by 13. Like, watch. If this is 1, this has to be 12 over 13. This has to be 5 over 13. The sine of k. Here's k. Opposite over hypotenuse. Make sure you understand this is the hypotenuse. It's never the adjacent. It's never the opposite. It is the hypotenuse. So, ka, toa. Sine of k would refer to 5 over 13. Okay, that is some decimal. Well, like, you could write this as 5/13 over 1. There you go, 5/13 over 1. If you have this angle k, you have to have this ratio. This divided by this has to be the same as this divided by this. This scaled is that scaled. It all works out. The cosine of k would be 12 over 13. You could write that as 12/13 over 1. Cool. Sine of j, here's j, would be 12 over 13. Cosine of j would be 5 over 13. Okay, now let's create another triangle. Why don't we just do it first with k? The tangent of k. Tangent of k is opposite over adjacent, 5 over 12. We can actually write that as 5/12 over 1. Now, what does that look like? Well, here is another triangle whose opposite is 5/12 and whose adjacent is 1. Oh, what did we do? We just essentially took this triangle and divided it by 12. This triangle is divided by 13. This triangle is divided by 12, which means this would be 13/12. It's like, that's kind of what we're doing here. Tangent of j would be 12 over 5. If you did tangent of j, you would have 1 divided by 5/12, which is the same as 12 over 5. All right, so understanding this, that leads us to like the essential questions of the day. If I give you the ratio of an angle in a right triangle, could you give me all of the lengths of that triangle? Could you scale that triangle? Okay, so it's like there is some angle H. H is an angle. This is very important. We will draw a right triangle with angle H. Make sure it's a right triangle. And you're told what the ratio is. It's 1/3. You can either say that's the adjacent over the hypotenuse, or you could consider the cosine of H being equal to 1/3 over 1, where 1/3 is the adjacent and the hypotenuse is 1. They're the same. 1 divided by 3 is the same as 1/3 divided by 1. So it's probably easiest to do that 1 is the adjacent and 3 is the hypotenuse. Now, why don't we find this missing side length? Cool. Well, a squared plus b squared equals c squared. I feel like we had the same one in your notes. B squared will equal 8. B will equal root 8. Root 8 is root 4 root 2, which is 2 root 2. Okay. Now, probably not scaled correctly. Probably needs to look more like this, but whatever. The sine of h, well, any triangle with this angle h, the sine would have to be opposite over hypotenuse, 2 root 2 over 3. Cool. Well, if you want to find the missing lengths of this triangle with angle h, well, since you know this ratio for h, you know all of the side lengths, you know all the ratios, and you can scale. It looks like the adjacent is going from 1 to 4. We'll scale this by multiplying by 4, which means this will turn into 12, and this will turn into 8 root 2. Now, you know what's fun? What if we did like the sine of this h? Oh, well, that's 8 root 2 divided by 12. Oh, that's the same as divide the top and bottom of 4, 2 root 2 over 3. Oh, yeah, of course. Like, they have to be the same. They are similar shapes, so they have the same ratios. Any triangle with the angle h will share the ratios. So let's say I divided everything by 3. Like, this triangle with the angle h will have the same ratios as this triangle, will have the same ratios of this triangle. Of course they will. Okay, we got Z. I always like to label my angle down here. This is an angle. So when I say the sine of the angle, I refer to the ratio of the opposite over the hypotenuse. Okay, let's find this one. So a squared plus 2 squared equals 5 squared. A squared equals 25 minus 4, which is 21. A equals root 21. 7 and 3 go into 21, but not 9. So I'm just going to leave this as root 21. Tangent of Z would be the opposite over the adjacent. Now, what's great about this is like any triangle with this angle C, all these ratios must be the same, or else they're not the same shape. They're not similar triangles. If I asked you, what are these lengths? Easy. Scale this, multiply by 4. If you looked at the tangent of Z for this triangle, well, like 8 over 4 root 21 is the same as that. Like, of course, the ratios of any triangle with this angle Z, whatever it happens to be, make sure you bring your calculators next class, will be the same no matter how big the triangle is, because they're similar shapes. We're just going to talk about these ratios so much, we need to have special words for it. Sine, cosine, tangent. All right, cool. Like, the rest should make sense. This might end up being a short homework if you know what you're doing. You could have also taken this triangle and divided it by 5. One, 4/5, 3/5. Great. It's like that could be scaled. That could be scaled. They're all similar. I can draw this triangle this way because you can kind of see the ratio of the adjacent over the hypotenuse is 1 to 5. So with this angle M, whatever the angle measurement will be, we will start to use angle measurements more in next class. So you will need your calculator next class. Cosine of M is 1 to 5. B. Excuse me. This is root 4, root 6. 2 root 6. Cool. Well, that means the tangent of M would have to be opposite over adjacent. Cool. And if this is 4, okay, great. This is 20. times 4, multiplying by 4. This would be 8 root 6. And now what's great is like a lot of people might do the following. And I'll go back and show you if you're interested. Let's say you did not do this. You did not do this. Let's say you use the Pythagorean theorem to find both sides of x. Okay. Let's say you did 3 squared minus 1 squared, and you square rooted that. Cool. And you were like, I like to use my calculator, root 8 over 3. That was like your ratio. Cool. I mean, that just kind of shows you that this is 0.942 in that triangle. You could have used the Pythagorean theorem here. Okay, right? So you got like 12 squared minus 4 squared. And you would have square rooted 128. And you might be like, oh, okay, so this is 11.313. This was 2.828. Okay, but like, watch this. Take this value, multiply it by 4. You know, like scale this triangle with angle H to make this triangle with angle H that is 4 times bigger than this triangle. Scale this by multiplying by 4. And oh, look at that. We didn't have to use the Pythagorean theorem. This would have just been this length times 4. Cool. And the same could have been done here. You could have used 20 and 8 and found this length, 20 squared minus 8 squared. And you got the square root of 336. Cool. But what I'm telling you is that you didn't have to use the Pythagorean theorem here. You used the Pythagorean theorem on the top one, and you got the square root of 21. And all you had to do is scale it. Multiply it by 4, because this triangle is 4 times bigger than the other triangle. And look at that. Square root of 336 is the same as 18.333. So like, scaling, guys. Scaling is the key. Scaling is a powerful. Similar triangles and scaling are powerful. All you need is one smaller triangle with the angles, and you know all of the bigger triangles with those same angles. Okay? All right, that's it. Peace.